Okay.
Good morning, my name is Fishy. I'm the PM for Fishy Consulting, and we're going to be going over our progress on the first subdivision project. So I'm leading the structural design, and with me today,
Andrew Vosberg, transportation lead.
Data Fish, environmental lead.
Hunter Kalaifel, water resources.
and then from here I'll go ahead and pass it off to Andrew to go over our transportation work.
All right, thank you, Ben. I'd like to begin by recapping my previous presentation, starting off with my scope. So we were first tasked with designing 2 new roads. First off is connecting the 2 discontinued ends of Ville Park Road, and then extending Old Oak Drive to meet that new road and create a T intersection. Second, we'll be designing a parking lot for Ben's senior living facility, and lastly, a walking trail that will span the full length of Ville Park Road and will be on the north side. All the values for the table on my right in the design criteria have been taken from the ASHTO Green Book and the NDOT Design Manual. And then I also used the City of Valparaiso ordinances and Americans with Disabilities Act to design the parking lot. Moving on to Ville Park Road, so you can see here we have the full horizontal alignment of Ville Park Road, and we followed the existing trail the whole way. Next, we have a typical plan sheet where you have the little sample of the horizontal alignment with the vertical alignment that follows it. And you can see the existing grade and the newly planned grade all on the bottom there. Next, we have Old Oak Drive, where we plan to go straight from the existing road and then have it bend to create a perfect 90-degree T at a perpendicular intersection. That way it's easiest for turning radii. Next, we have, then again, a typical plan sheet for Old Oak Drive, where we have the horizontal alignment on top and the vertical alignment below with the planned and existing grades. Next, we have the intersection, where we have a stop-controlled intersection with Old Oak Drive yielding to Ville Park Road. The turning radii are 50 and 35 for the entrance to the parking lot. And then all the taper and storage lengths came from the NDOT Design Manual, and there is no deceleration length based on the speed limits being pretty small, and the data we were given for the traffic was pretty low too. So we decided not to use deceleration lengths. Next is the parking lot. You got the building east of the parking lot. All the parking spaces I got from the City of Valparaiso ordinances on parking, and the disabled parking spots I got from the Americans with Disabilities Act. And then we have a sidewalk also leading up to the building from the walking trail. And we got the cross section, as you can see for Ville Park Road on the top. You have 3 12-foot lanes and then a 4-foot shoulder. And then Old Oak Drive, you got 2 11-foot lanes and then a 4-foot shoulder as well. There are no curbs, so I really felt the need to have a shoulder also to accommodate ambulances. Being a senior living facility, they tend to see those every now and then. Lastly, I'd like to go over my future work. I will be continuing my CAD drawings as far as like labeling. I got to label all the curves for my vertical profile, and then I also got to label things like crosswalks and put hash marks and whatever's needed. And lastly, I will be getting my cost evaluation all set for the final report and presentation. Next, moving on to Hunter with our water resources.
Okay, so I'm going to be taking you through some of the progress I've made so far in relation to water resources. I'm going to start off by going over the scope again. So the scope as presented requires that all local regulations be followed while utilizing LID methods of design. LID stands for low impact development. The client also desires that 80% TSS and 50% total nitrogen load be removed from the water. They would also like 1.25 inches of rainfall from all impervious areas be treated as a water quality volume. The scoped area is in red in the figure to the right. It doesn't include the entire roadway portion of the design because it would just become repetitive. This figure to the right shows the final plan design. It utilizes a vegetated swale on either side of the roadway to treat the water quality volume for the roadway portion of the design, and it drains to a dry pond at the west end of the plot. And then the building portion of the design uses 2 rain gardens for water quality and drains through grass swales to a wet pond where the flood control volume is handled. The rain gardens both have upturned elbows, and the wet pond has flowing treatment wetlands, which will be able to sufficiently remove nitrogen from stormwater runoff. So for the vegetated swale design, it was first designed for water quality, and the 3-month, 24-hour storm was used as the water quality storm. The city of Valparaiso requires a maximum, specifies a maximum depth of 4 inches of water, side slopes 4 to 1, horizontal and vertical, and then a maximum water velocity of 0.9 feet per second in order to achieve the treatment necessary. So a 5-foot bottom width for the vegetated swale was selected based on those. And then the swale was also designed as a flood control to handle the flood control flow, and the depth necessary to handle it is 1.25 feet, and then an additional 6 inches is required by the city of Valparaiso for freeboards, so it brings the total soil depth to 1.75 feet. Check dams will also be used within the swale to ensure that the water velocity stays below the 0.9 feet per second limit, and check dams will help to encourage infiltration and provide a water quality volume. The check dams are going to be made of 6x6 timbers, and they will reach a total height of 9 inches. Behind the walls there will be riprap rock to prevent soil erosion. The check dams will be spaced at 37.5 feet, and a total of 66 check dams per swale is necessary. For detention pond design, an inflow hydrograph needs to be produced using the WinTR55 computer program. So utilizing curve number, time of concentration, and rainfall intensity, the inflow hydrograph as seen in blue was produced. Next, the maximum allowable release rate based on the city of Valparaiso regulations of 3.1 cubic feet per second was determined because the allowable release rate is 0.5 cubic feet per second per acre of developed land, and the roadway portion was 6.2 acres. And then finally, for the dry pond, a pick and bottom outflow structure was selected, and level pool routing was performed to determine that the outflow, as seen in orange, was less than the max allowable outflow. The dimensions. So the level pool routing and the inflow hydrograph was performed for both the dry and the wet pond in the design, and the storage volume length and width for the dry pond is 150 feet by 75 feet with a max water depth of 4 feet. And then for the wet pond, the length and width was 300 feet by 125 feet with the max water depth of 0.5 feet. It should also be noted that for the wet pond, it's required that between 3 and 8 feet of normal water pool below the storage is required to maintain the quality of the pond. And then the total storage volumes for the dry and wet pond is 74,000 and 19,000 cubic feet respectively. Moving on to future work, the 2 rain gardens on the building plot still need to be designed along with the filter strip and their locations. These are quite simple. The filter strip is quite simple to design as it's just grass, but it's necessary in order to ensure the performance of stormwater VMPs. Many CAD drawings still need to be performed in order to better illustrate the ideas of the final design. And then some culvert design is necessary to continue the flow of water in the swales below the roadways where those intersect. And then finally, once all that is done, a cost estimate will be performed. So now we'll move on to environmental.
Good morning. I'm Dana Fish, and I'm the environmental lead for Fishy Consulting on the Brooks Subdivision Project. And I've been responsible for designing a wastewater collection system, a lift station, and a bank stabilization method. And so today I'll just be going over a bit of what I've been doing the last few months and just a progress update. So the last few months I was creating various alternatives for each of these tasks. And as a result, I will be selecting a gravitational sewer system composed of concrete pipes and sanitary manholes that will feed into the lift station. This lift station will be located on the west side of the Brooks subdivision as it is the lowest point of elevation on this plot, and its location is relatively close to the proposed roadway, allowing for easy access. And then the final piece of my scope is that I will be designing a green logs vegetative slope facing system, which is a soil erosion control system, courtesy of Filtrex Technologies. And as you can see on the screen, this is my design schematic, and added to this schematic in green is the green logs vegetative slope facing system on Beauty Creek. For the design of each of these tasks will be dependent and guided upon certain design constraints and assumptions. First, starting off with the lift station, it is important that for the design of the force main, that selecting a proper material that will be able to withstand the constituents of wastewater, so corrosive gases such as hydrogen sulfide, oil, grease, and should be able to handle those items. And it is also important that the pipe flow velocity within the force main remains at a minimum of about 2 feet per second. And so for this, I will be selecting grade work, waterwork grade ductile iron as the pipe material, as it is strong, durable, resistant to damages, and will be able to prevent potential contamination from water and sewer lines. Moving on, I'll also be needing to design a wet well, and so the size of this wet well will be dependent upon the average design flow of the system, as well as keeping a retention time of a minimum of about 30 minutes, and this is a standard recommended by the 10 state standards as well as the city of Valparaiso. And then in addition to the lift station, multiple pump units will be needed, and so for this, it is important that the units in this lift station should be able to handle capacity. Should one be out of service, the remaining units should be able to handle the peak hourly flow. Moving on to the green logs vegetative slope facing system. This design will be dependent upon the potential site evaluation of Beauty Creek, and some of this will include gathering data about the hydrology of the area, soil properties, the geometry of the bank, vegetation, and watershed characteristics. Now, much of this information will probably need to be assumed, and this will be addressed later in future work. I'm also going to assume that this design will be applied to about 100 feet to 100-200 foot section of Beauty Creek itself, and that the bank slope will be a ratio of its vertical distance to its horizontal distance. And then finally, the gravitational sewer system has its own design constraints and assumption. First, I'm assuming, and one of the design criteria that I'll be keeping to is that the sanitary manholes would be concentric, as is required by the city as well as the 10 state standards. They would be about 300 to 400 feet apart, And then it'll be also 48 inches in diameter, as it is a standard manhole size. In addition to that, the minimum depth that the sewer lines would be under the proposed roadway would be about 3 to 3.5 meters, as it will help keep a good separation between water lines and sewer mains, and if there might be potential underground facilities along the way. For the pipes, as I said before, this gravitational sewer system will be made of concrete pipes, so in that they should be kept at a pipe flow velocity between 2 and 10 feet per second, and to ensure that this remains in the proper velocity range, the pipe slope will need to be at a minimum of about 1%, and this was calculated using Manning's equation, which is for open channel partial flow pipes. And I'm assuming that these pipes would be flowing in half full to ensure that this was assumed because it should be able to, I'm designing it this way because it will help the design so that it can handle the peak discharge, but at the same time, it should be able to help the efficiency of the gravity flow system, and should the subdivision ever expand, it should be able to handle those new expected flows. Moving on, these, as I said before, I did pipe slope calculations using Manning's equation. So this is the equation that I used, and then I plugged it into Excel. First, using a slope of 0.22, as it was recommended that for 12-inch diameter pipes, a 0.22 slope was used, but I found that it would not be able to handle the peak discharge of the subdivision, and it would have a pipe velocity of 2.3, which I deemed to be unsatisfactory for this design. So I'm going to go with a 1% slope, as it'll have about 5 feet per second in the pipes, and it will be able to handle the peak discharge at about 0.055 cubic meters per second. So I've also been working in CAD to come up with drawings to show the plan design, and so this is a plan layout of the gravitational sewer system of Vale Park Road and Old Oak Drive, and hopefully you can see this, but there are manholes shaded in yellow at each end of the streets and at each change of direction in the road, and especially at the intersection of Vale Park Road and Old Oak Drive. This is a blown up view of the intersection. To note that this structure is a little more special than the other ones because this is the one that will be connecting both pipe networks to make it one. This one has about 3 connections. This structure has 3 connections in it, and the flow should be flowing west towards that lift station. And this is a sample profile view of Vale Park Road. This shows structure 40, which is that intersection. And in pink is the proposed roadway, thanks to our transportation lead. And the red shows the existing ground level. And in green is the pipes, and the concentric manholes are the vertical structures, as you can see there. So the future work I have to do is creating a detailed drawing for the sanitary manhole, as well as verifying that my gravity sewer system runs smoothly, as well as working on verifying head loss calculations for the pump system and selecting a pump and figuring out how many pumps I might need for this design, as well as continuing the force main design, which will include using Hayes and Williams equation for that, and as well as just continuing to work in CAD and creating a pressurized pipe network. For the Green Lines vegetative slope pacing system, I will be needing to address the site characteristic assumptions so I can continue this design, as well as working in CAD. And then, of course, I will be working on environmental costs for the total of this and coming up with a detailed cost estimate for key design components. And with that, I'll be transitioning over to our structural engineer.
All right, thank you very much. So first, to just kind of go over a background of the design, we're going to be providing complete structural design of this structural steel frame building with reinforced concrete slabs, and then with some additional components provided as kind of discussed already. There will be a overview architectural layout, which will give some key facility information, as well as provide information required to generate our member layout and what we're going to need to design for. And then wastewater and water treatment, as well as a parking lot, which were discussed in the previous sections. So as I mentioned, that architectural layout, I think we've seen this before in the last couple of presentations, but this is our first floor, which isn't quite as pertinent to the structural design as our second floor, which we'll be gathering our loadings from. So this is the chart of different loads I need for the building. The main ones are the public spaces and corridors at 100 PSF, as well as the living spaces at 40 PSF. The snow load I took is from ASCE 722. The rest of the design is from ASCE 716. This is just my reported snow load right now. The issue with ASCE 716 is that the area we're in is in a case study zone, which requires site-specific research to report an actual area load for the snow. So I think that this 722 uses a couple different factors differently than 716 to come to 60 PSF, so I might be reevaluating and making an educated decision on a different load to use, and use 716 standards to design too. We are in risk category 3 because it's people are always going to be in the building. It's sort of there will be medical staff and just an at-risk population in there already. All right, so for our member layouts, we have girders in green, columns are the squares, and beams are in red. It's pretty regular until you get into this section, which, if you remember from our architectural layout, this is going to be a stairwell, and then there's going to be an elevator here. So that's why we start to get some irregularities from the pattern. Roof, it simplifies a little bit, and we see a beam going over across the top of the stairwell, and then also for the roof, the area load is constant, so we don't have to worry about too many changes in the loading pattern. So as far as beam design so far, first we go through, take the tributary area of the beam, so what that beam is going to be responsible for supporting. For my example here, I included just one of the beams that supports purely the loading from one of the living spaces. So we find the tributary area, use our equations to turn that into a line load, and then find the max moments. And once we have that moment, I would use table 323, from the AISC manual to find the lightest W shape to support the area. And then once I had a bunch of different selections, I sort of grouped them into, I grouped them to be a little more economically efficient, which we'll see on this floor. This is what this column second from the right is the theoretically most efficient shape, but just to shrink the bill when we get down to it, I grouped them into, there's 3 different shapes here, just to be a little more efficient when it comes time to actually order the steel. So that's for the second floor, and then moving on, this is for the roof beams. Girders was really the same process. The only thing that changed was I took the total tributary area for the beams that the girder is supporting to find a total point load, because instead of an area load or a line load on the girders, we're going to have 2 point loads. So it's sort of a different pattern. But other than that, everything's the same. And then the results are shown here. That orange color is, and this was the same with the beams, is to show that it's been changed from what was decided based off the initial design. That's just for economic efficiency, like I mentioned. And this is the roof. I did it a little bit differently and just grouped as I was designing here. Last is for the girders. It's really the same process, except we're going to be using a different cable when we come down to it. But that takes me to my future work. So we're going to finalize that column selection, evaluate the use of angles near the holes in the slabs and near the stairs and elevator, just because they're not supporting as much of an area. So use angles potentially for flexural support in those areas. As far as lateral design, I'm going to be evaluating a brace frame versus a masonry wall to provide the lateral support. We're going to perform our analysis in RESA, and then once we finalize the design, we'll be able to estimate the total costs. And with that, I'd like to open the floor up for any questions.
Okay, let's start with you, Ben, and I just want to check, this is a knowledge check, and because you talked about the snow loading and the ASCE 16 versus like the 22 in there, and you're going to go back to the 16. Can you tell me what's the difference? If not, I will tell you in there. So I'm using the ASCE 22 versus 16.
I'm not sure if I have an exact theoretical answer to give you. I know they made a lot of changes to how they theoretically proposing it, and I think
of the combination equation, the load combination equation. So what was the multiplier in ASCE 22 versus like 16?
I think in 22 there's a lot more that's already been factored in, so it may be at just 1.0, and then 16 is at 1.6.
That's correct, yeah. That's why you have the hazard tool, and so the multiplier is 1.0 in 22 versus like 1.6 in ASCE 16 in there. Now, that's actually, why did you say that's a special case study like zone for Valpo versus like if we go back to Tuesday, when they were presented, they were able to come up with those snow loading, at least if I recall correctly, was 45 something.
Was this for the
Brooks?
It was also for the Brooks?
Yes.
I'm not personally sure how they got to their number. But.
Okay. And any constraints on the depth of the W sections in the, from an architectural point of view, how deep you can go?
Not at this time. I generally try to keep myself below like 18, 20 inches, say, if possible, but there's no physical constraints that I know of yet.
Okay. Then on slide number 25, you showing the minimum depth below under the sewer system, like 3 to 3.5 meters. Is that correct, or feet?
Meters. It should be about 12 feet
Why?
to allow for any potential construction for underground facilities.
What?
This was in the 10th state standard.
What underground facilities to be constructed?
Basements. Basements for subdivisions.
Well, you are in the right of the way, correct? You're not doing
Correct,
the,
it will probably not be this way anyway in my design for the way it's, just the elevation and the low points.
I'm not sure that's true, because in there, you're not gonna go that deep. You know that your cost will be extremely high if you go like 10 feet, like 3 to 3.5, 10 feet below. If you don't have to, of course, there are some times where the topography dictates. Okay, there, well, that's the clarification. I think that takes me back to Andrew, and then maybe I'm gonna go back to Hunter. Andrew, on your plan view, or actually the profile of the road, where you show the existing versus the proposed, like
Yeah, I know it's hard to
elevation.
see, but this
Yeah, I
would
can
be
see it.
the planned grade line, and this is the existing. It's much easier to see in the report in the plan set than it is to show on screen.
Now, how do you come up with the planned or proposed elevation? Do you do like a cut fill balance type of calculations, or
There's
how
no calculations based on, I mean, I try to keep it as close to the existing just to minimize, having to fill a bunch or cut a ton. What I would do is, they have K values which determine like the slopes in the road, so I try to keep it as straight as possible. And then if there's like a dip in the existing grade, I try to go down to, so you don't have to fill a ton. But then I gotta keep it within the K values shown in this table. Or,
I think my question is, how do you do it? I mean, in my old days, when we did this, it's just I want to balance the cut and fill. So I do not want to be hauling any dirt out or bringing anything in now.
It was just connecting at the ends of the, starting at the elevations where the existing roads are, and then keeping it as close to the existing grade as possible while staying within these values. So I just try to keep it on the existing line.
I think Hunter wants simple question for you, because you may open my eye to a Valpo ordinance. You said that the velocity in the swell is less than 1.9 and the depth of the water is 4 inches. Is that for conveyance or for BMP, like a treatment? If I am using the swell for conveyance, am I sticking to those numbers?
Yeah, that's like specifically for like a vegetated swale to because you want to get like good water quality treatment. So that is like, in order to accomplish the water quality treatment, those are like the regulations for that specifically.
Well, how about if I'm using a vegetated swale for conveyance?
Yeah, conveyance is different. Like the regulations are different for conveyance versus water quality treatment.
And what is it, if you recall, for conveyance? If you're just using a swale to convey water, like roadside ditch, that's a swale, and so do we have to stick to the 4 inches?
No, it can go, well, if you go back to it, like the flood control depth was 1.25 feet, so you can go above 4 inches. The 4 inches was just specifically so you could get water quality treatment.
And are you maintaining that in your design?
Yeah, for the water quality side, yes. But then for flood control, you can go above 4 inches.
Thank you.
Since you're answering questions, Hunter, I have one question. And that's for your wet pond with the floating treatment wetlands. How are you going to maintain water in there? Is the water table that high, or are you going to need an impermeable barrier underneath the wet pond? Or
Yeah, so like if I think the water table's low, so we're gonna have to implement an impermeable barrier to keep the 3 to 8 feet water level within the pond.
Okay. And I guess one other question: Are you designing the treatment wetland and the plant selection and all that, or?
Oh yeah, I'm gonna be designing the flood.
Okay.
Any other questions?
I have a question for Hunter about the check dams. Is there a particular reason why you chose them to be timber instead of riprap or something? Because I'm imagining wood would degrade over time?
Well,
Or
the,
away?
like, other alternatives were like concrete or like rocks. So those are like, if the vehicle goes off the road, it's more of a safety hazard
Okay.
versus like the timber, the timber alternative. Plus, timber is probably a cheaper alternative.
Okay.
I always like to think about how roadway and water collection work together. So your detail of the vegetated swale, the ditch that's gonna collect the water off the roadway, had a specific dimension. So it means if the road's going this way, that's great. The water's gonna flow down the hill, but as soon as you have a sag, well, you know, now you're gonna collect water, it's just gonna sit there, so. Normally, on a roadway profile, you would show the ditch profile also, rather than it being a constant, this far off, this far down, you know, if you run into a sag, you may have to adjust that grade, so I wonder if you're talking to each other about how you're gonna get the water all the way down to the creek. Because I know that road, it goes up and then it goes down, so, you know, you need to figure out what the grade of that ditch is. So you two guys need to talk to each other, mostly a comment.
So, you know, for the most part, from the west to east side, the difference in elevation, I think it's almost like 20 feet, like it's pretty, for the most part, gradual, so I mean, I try to keep with the existing grades, because for the most part, it's from like, I think like high 600s to like low 700s, I believe, on the east side, so for the most part, we just try to kind of keep it level. But there would probably be some points where
Yeah,
you know, spot.
it's just something to think about, I think. You know, that ditch needs to flow.
I have questions for Alex, mostly, because I don't dare to get into the other stuff, so.
Andrew?
Or Ben.
I'm sorry, Ben. Yeah, Ben, sorry. Yeah, so my first question is, how did you decide that the risk category is going to be risk category 3? It's a senior design facility, right?
Senior living, yeah.
Yeah, so how did you decide, what did you use to define, determine that risk category is 3? Did you use AAC
Yeah,
7 or?
716, yes.
Yeah, so I would suggest, because AAC 7 has like a general definition of those risk categories. You might want to consult International Building Code, because I think in chapter 16, we have like very detailed definition of those. This facility, based on the number of the people, number of the occupants, it might fall into category 2, which makes the life much easier for you. So the second question is that if you can go to the structural layout. Yes. So I see some of the red lines. I suppose what are those red lines that they are not over any columns or something? For the first one on the left-hand side, you say 10 feet typical.
Oh,
It's just sitting on the
this
B.
area?
The first one is just the second red line on the left-hand side.
You're
Yes.
talking about this?
Yeah, what is that?
This is, the red lines are beams, and those are feeding directly into those are attached directly to the girders rather than,
So those beams are going directly to the green ones are the girders.
green are the girders, and you'll see every grade is in line with the column. We have 20-foot and 30-foot spans for the girders, and then the beams are spaced at 10 feet.
Okay, so can you tell me what is the direction of the columns based on the weak axis and strong axis? Let's say you're using the I-shaped beam, I-shaped column. So which direction you put the I-shape?
I mean, I haven't made an official decision. I imagine it would be more ideal for connections to run the weak axis this way, so the girder can go directly into the web.
Okay. Thank you very much for that. And then you also mentioned that we have talked about it, so I'm not going to ask too many questions about the lateral load resisting system. But you said that it's a possibility that you use shear wall masonry.
Yeah. So
With the size of your structure, do you think you should use reinforced concrete shear wall or masonry shear wall?
I mean, either is a possibility. The main reason I bring it up is because for different fireproofing measures, often the stairwell and the elevator are cased in a masonry wall to provide.
And you're going to use them as lateral resisting force system?
Yeah, because I may already need them for the stairwell and elevator shaft. They can pretty easily provide a good amount of lateral resistance, so it should be considered if they're going to be.
Okay, so what's your strategy, because those are like small areas, what's your strategy if those shear walls, masonry shear walls, doesn't provide enough resistance for lateral force or for the stability? Are you planning to add something to the system?
Yeah, I could potentially add a braced frame from there.
Oh, okay. So, okay, thank you.
Thank you.
And then, the next question is that, in several places on the presentation, I see that you mention AISC and then name a table.
Yes.
This is just a suggestion. First of all, some of those tables I would suggest check the table numbers because.
Yeah, if there was a typo, it should be.
Yeah, it might be a lot of typos there. But also when you use a table from the manual, we generally mention that this is from steel construction manual, because when you say AISC, everybody thinks about like the specification, not the manual.
Okay.
So mention manual. And another suggestion, the last thing I'll let you go, and this is just general for the presentation. We are like, hypothetically, your client, and this is like towards the end of phase 2. In some of the slides, I saw that you're still using, for example, for the limit of the project, you're using the word approximate. Again, this is just a like friendly suggestion.
Sure.
This doesn't look good towards the end of phase 2, that you're still using approximate limits of the project or something. So maybe we should update, as we go forward, update the slides.
Sure. Thank you.
Thank you very much.